Welcome to another lesson from Transparent Physics. This is our first lesson in our gravity and orbit unit. And I thought we'd start with a little bit of historical perspective regarding theories of how the planets were set up and orbiting in our solar system. This is important to know what people thought because we're going to spend some time on Kepler's three laws, and to understand their significance you really need to sort of understand where we've been. So I call this lesson Theories of Orbit and the Fantabulous Emancipation of One Planet Earth. And these are based in developments in Western culture. The Arabic world will make a guest appearance in here as well. Okay, so let's go back in time. Specifically, 400 BC. And 400 BC, we've got some natural philosophers, as they say. And our first fellow is Eudoxus. And he proposes, first of all, a spherical Earth. So the idea of the Earth being a sphere was not new to Christopher Columbus. And in addition, not only is the Earth a sphere, it is also what we call geocentric, in the idea that surrounding the Earth was a system of transparent spheres, and those contained all the other things that we see happening in the sky. And that geocentric model makes sense. I mean, if we don't feel the Earth moving or spinning or anything like that. So the idea is that, when you look up in the sky, it seems like the sun moves around us and the stars spin through the sky. And sometimes a couple of the stars look kind of weird and don't really follow the direction for the other ones. And we came to understand those as planets, and there was comets and occasionally some things. But generally speaking, it was a safe assumption that the Earth was at rest and everything was moving around it. So adding to that, Aristotle ran with Eudoxus's ideas, and also considered the idea that things in the heavens must be perfect and unchanging. Obviously, if they're perfect, they don't need to change, and the Earth itself is imperfect and changing. So he made a distinction. And he said, this is a pretty good system here, but let's recognize that the Earth is not governed by the same rules that governs everything else around it. And this idea that the heavens, that space, represented this perfection that we would not be able to achieve here on Earth, colored a lot of thinking for a long time. It's sometimes hard to distinguish the idea of space from the heavens. And there's a lot of extra connotations that come along with looking at space that we've dealt with throughout the millennia. All right. Now, in addition, just for the record, at the same time in the same place, there was another guy, one of Aristotle's peers, by the name of Aristarchus. And he said, hey, you know what? Why don't we look at it as if the Earth's orbiting the sun? And he was greeted with no respect for his idea. So, again, back in ancient Greece, they'd already figured out that the Earth was round, and somebody proposed that the Earth moved around the sun. So, hey, progress, right? All right. Then, as we continued to look at the stars and make observations, we're running with Aristotle's idea that everything's perfectly in circular orbits, because circles are perfect. Everything in space is perfect. Circles are perfect. So everything must be moving in circular paths. That was Aristotle's idea. And as we studied the skies more closely, it became hard to match some of what we were seeing with a very literal interpretation of Aristotle's ideas. So people were wrestling with this because Aristotle was very well respected, but what we were seeing was not matching the theories. So in comes Ptolemy. around 150 AD. And Ptolemy liked Aristotle's ideas. He agreed with the geocentric model, but they could not account for observations just straight with Aristotelian theories. So some of the things that gave Aristotle's theory a problem, there's something called retrograde motion of the planet, where a lot of times when we see planets, they'll sort of track across the night sky. Every time you look at them, every night they're getting a little further along. Some planets would track across the sky and then slow down and then speed up. Or some planets would trace across the sky, slow down, and then even like do a little loop-to-loop backwards for a little bit, and then keep moving in the direction that they were. So that was hard to understand within the strict context of everything moving in perfect circles, as Aristotle suggested. There was also very clear variation in the brightness of planets, depending on where they, what time of the year it was, where they were in the sky. Planets at times appeared brighter and dimmer, which would seem to imply that the distance is changing. But that can't really be accounted for in Aristotle's theory, where everything is orbiting in perfect circles around the Earth. So things like that made astronomers a little worried about the Aristotelian ideas. So Ptolemy came in. Now Ptolemy is still a Earth-centric, a geocentric model, but he is a smart cookie. Right? And he uses a lot of geometry to come up with fixes for these problems. And so I call his fixes the 3 E's: eccentrics, epicycles, and equants. Real quick summary of each of these ideas. And again, these were all designed to try to come up with solutions to the problems that we were seeing when we actually took better data. First of all, when Ptolemy is credited for having a geocentric model, that's actually not entirely fair. He moved away from Aristotle's idea. Aristotle and Eudoxus had the Earth at the center. And Ptolemy said, well, you know what? We could take the Earth a little off the center. By putting the Earth off the center and having this still rotate around the Earth, just sort of wobbling around a little bit. It's still a perfect circle. It's just a little bit off center. Ptolemy could account for some of the observations he was seeing in the sky. The next thing he had is what's called an epicycle. Again, he was still working with circles. He still liked circles. But he said, hey, what if we have a circle on a circle? So as a planet is orbiting around, it is not just orbiting in a circular path, it is traveling on a circle as it goes in a circular path. And then this creates a more complicated motion. I don't know, when I was a kid, we had something called a spirograph, where you put a circle in there and you sort of spin it around. That's dating me. Many of you might have to ask your parents about that, a spirograph. But it was what we had for entertainment back in the day. So this could account for more complicated motions, and if we needed to, we'd put an epicycle on an epicycle, so you could keep on continuing this as you need to. The hardest one is an equant, and the idea is that Ptolemy felt that planets were not moving at a constant speed. One of the things that Aristotle said is everything is perfect and unchanging. Unchanging means the speed's going to stay the same all the time. And Ptolemy's like, I don't think they do. So he came up with this idea of imagining that instead of the center of the circle, imagining a point off center. And while the speed may not be constant, the angular sort of velocity was constant. But depending on where this was centered, a constant angular velocity would mean that this is traveling different distances for different angles. If it's closer to where this pivot point is, if it moves 45 degrees, it's not going to move as far as if it's further away from that pivot point. So he was able to explain why he felt the planets were speeding up and slowing down with this arrangement. Now, other people that looked at his ideas they were like, we can buy this. This isn't too crazy. this isn't too crazy, circles on circles and stuff like that. There were some people that had issues with this idea because, again, it did challenge Aristotle's idea pretty directly that everything's unchanging. So people weren't as happy with this, but the model solved a lot of the issues that were with the Aristotelian system. Now, again, remember, it's still wrong because obviously the Earth's not at the center. But it really tidied things up. I mean, Ptolemy was a smart guy and made very smart, reasoned approaches based on observations to try to come up with an explanation. So, I don't know, sometimes I think we kind of poo-poo the geocentric model as being kind of silly and ignorant, but there's a lot of smarts that went behind developing this and making it work. Now, again, as I noted, these ideas went a long way to dealing with a lot of the issues that the Aristotelian system had, the geocentric model had, and Ptolemy published these ideas in a work, a very significant scientific work called I think it's called the Almagest. Again, sort of one of the most important science books in the history of civilization. And but when Rome fell, a lot of Europe sort of fell into the Dark Ages, and there wasn't a heck of a lot of science and deep thinking being done for a while. A lot of the intellectual ideas, including this, the Almagest, actually found its way into the Islamic world. At the time, the Islamic world did not suffer the same sort of intellectual decline that Europe sort of faced at the time, and they had sort of a renaissance in thinking in libraries and communication with other cultures, and really expanded on a lot of mathematics and science and stuff like that. So they took the Almagest, incorporated it into a lot of their ideas. It was translated and expanded upon, and eventually it was reintroduced to Europe, I believe, through Spain in around the 12th century. And then it sort of was discovered again by Europeans. But we do owe those scientists, those Islamic scientists, who preserved this information until Europe was sort of ready to handle it again. All right, so now we got a big time jump. We're going to go all the way to the 1500s. So, 1500s. This is a name that you maybe have heard before, Copernicus at this point. If you haven't heard any of these other guys, here's Copernicus. Copernicus gets credit for considering a heliocentric model. Again, remember, he was not the first person to come up with this idea, but he's given credit for developing it a little more thoroughly. Now, Copernicus had some issues with with Ptolemy's model of the planets. Again, if you remember, Ptolemy had to get the speed of the planets changing as they orbited. And that really grated Copernicus's cheese. He hated that idea because he's like, that's not what Aristotle said they did. Aristotle said everything has a nice, uniform, constant speed. And that's perfect, and that's the heavens, and Ptolemy is getting it wrong with this speed changing. So he wanted a system where the speed didn't have to change. Plus, there were problems afoot. The Julian calendar, which I'm not blaming on Ptolemy, it was developed, back in the Roman Empire, and problem was it wasn't a fantastic calendar. It was some of the assumptions were wrong. So basically, every year it was off by about 11 minutes. It added 11 minutes every year. It was too long. And over time, when we're talking about centuries, 11 minutes a year adds up. So we're talking about days and days that were being extended, and that was changing when certain holidays were falling. Specifically, the Roman Catholic Church was having an issue with this because they were trying to plan for when they wanted Easter, which I think was based on the vernal equinox. And basically, Easter kept on getting earlier and earlier and earlier in the year as the centuries passed, and the Roman Catholic Church was not happy about this. And they enlisted some people to... They threw some money at the problem and tried to get some smart people to look at this and figure out why this was happening. So they were open to other ideas that would help solve this significant logistical issue they were having. So Copernicus sort of starts back at the Aristotelian model again and says, hey, let's keep perfect circles and let's keep constant speeds. But in order to do that, he had to get rid of the geocentric model and put the sun at the center instead. And he kept Ptolemy's idea of epicycles, because this wasn't perfect either. There still was issues. So he says, sun at the center, bring back perfect circles, bring back constant speeds. So he was trying to harken back to the Aristotelian system, but sort of updated, sort of version 2.0 based on stuff that they had learned. While this is a smoother model for a lot of reasons, putting the sun at the center is obviously right and solved a lot of problems that were sort of artificial constructs of putting the Earth at the center instead. It really didn't do that much better of a job because some of Copernicus' assumptions were still wrong. We weren't talking perfect circles. We weren't talking constant speeds. So when he tried to fit what we saw to his theory, it really was not significantly better in many regards. In some places, it was worse than the Ptolemaic model. And also, besides the fact that it simply wasn't a significantly better model in and of itself, the fact that we took the Earth away from being the center of everything also, again, was upsetting to a lot of people. There was a lot of theological significance to the Earth being at the center of everything, and having the Earth just being another rock orbiting the sun sort of took Earth out of a special place that it used to have in the position of existence. Now, he did publish this in 1543. If you notice, it is also the year he died. So, well, I guess I'm off screen when I pointed at that. Copernicus died in 1543, and this book was published in 1543, where he announced his system. He was concerned about how this idea would be received, even though he had the best intentions for it. He actually dedicated the book to the Pope. And I think his publisher, after his death, put like a different forward on there, basically saying, hey, this is just a mathematical construct. It doesn't necessarily represent reality. We're just trying to figure out some sort of system to fit, observations. But we're not saying this is necessarily real. There's no reason to believe Copernicus didn't feel his ideas were real, but it just shows that people were worried about offending the Roman Catholic Church at the time. So, Copernicus is in the mix. Again, his ideas are not immediately embraced, but they definitely do shake up the system a little bit. Okay, so 1543, Copernicus dies. 1546, Tycho Brahe is born. Tycho Brahe is, I believe, a Danish astronomer. And he is sort of the last of what we call the old school astronomers. He didn't use a telescope. Telescopes were invented, telescopes were improved upon by Galileo, used for astronomical observations by Galileo. Tycho Brahe did not use a telescope. He made ground-based observations using like sextants and astrolabes and stuff like that. He looked at positions of objects. He was a very, very good astronomer. And he had a lot of money behind him. He had several wealthy patrons over the time. He sort of came from money himself, and he managed to get himself assigned to wealthy patrons who would support his endeavors. I believe a lot of the times he sort of paid his way at these estates by doing horoscopes and making predictions and things like that. But the idea was that he had arguably the best astronomical observatory in the world at the time for what was considered to be a great observational observatory. And he moved around a couple times, but he was an outstanding observational astronomer given the technological restraints of his time. And he took decades and decades and decades of positions of planets and other things in the sky in an effort to develop what he wanted to call the Tychonic model, where he sort of would blend elements of Copernicus and Ptolemy together into his own ideas. His model never really took off, but he wasn't an unsuccessful. Again, his observational astronomy was very significant. Even if he didn't necessarily have good theories to go along with it. Of feathers in his cap, he did make note of this, what I understand to be the first real recorded supernova, like scientifically done. And this demonstrated the idea that space was not immutable and unchangeable. Things can change in space, even stars. He also was able to observe comets well enough to recognize that if there were these celestial spheres, that the comets were moving through them, that they were not staying like in their lane, they were crossing across spheres. So also a fun fact, which is true to the best of our understanding, he did actually lose the tip of his nose. The sort of the fun fact about Tycho Brahe is that he had a fake nose, and the story goes that he got in a mathematical argument with somebody at a bar after they'd been drinking and challenged the guy to a sword duel, and ended up losing the tip of his nose in a sword duel, and did get a brass nose made as a prosthetic and sort of stuck it in there. And but good news, he and his opponent, which I seem to remember reading was like a distant cousin, they made amends, so they did not stay angry at each other, and he did go about wearing a brass nose for the rest of his life. So, in comes Kepler, and this is the final stretch here. So Kepler, 1571 to 1630. So if you compare that to Brahe, Brahe was born in 1546. Kepler was born in 1571. So Kepler younger than Brahe, definitely. Kepler was a very gifted mathematician, very religious individual as well. And Kepler was convinced that by studying the universe, by seeing how things worked, he was understanding the mind of God, in the idea that if God designed the universe and we come to a better understanding of the universe, you're coming to a better understanding of God. So he made a zealous effort to understand the universe, because he thought it was the key to unlocking a deeper understanding. And also, he was really into geometric shapes. He loved geometric shapes, and those colored a lot of what his thinking was throughout his academic career. He had a tough life. Brahe was a very wealthy guy, lived a good life for most of his life. Kepler, relatively poor, had to move around a lot, lots of family misfortunes, very different sort of odd couple kind of individuals, but he really worked through it to make some important contributions. And so Kepler ended up becoming an assistant to Tycho in 1600. Now Tycho dies in 1601, so Kepler and Brahe's partnership didn't last a super long time, but he knew that the data Brahe had been collecting was essential to analyzing his own theories and defending his theories with actual data. I'm not going to get into the details about how Kepler ended up with Brahe's data after Brahe's death. There's no evidence of foul play. There's a couple sort of internet rumors about Kepler being responsible for Brahe's death, but they exhumed the body. They didn't see anything about that. It believed it was basically a medical issue where he passed away, and Kepler was able to get access to the volumes and volumes and volumes of astronomical data that was the life work of Tycho. And again, now there is a little bit of intrigue about the details of how that happened, and there were some legal issues associated with it, but regardless, Kepler was able to have the data and analyze it, and he pored over it, and he was looking for evidence of his geometrical interpretation of the universe. And when he came down to it. He wasn't looking to revolutionize things. He just wanted to tweak it with his own sort of geometrical overlay upon it. He was very much a Copernican and wanted to develop and further that idea. But as he studied the data, he could not get the data to behave the way he wanted it to for his models. And he realized that he was going to have to take his ideas and basically throw them away and start over. Now, what he ended up with when he was done will be the topic of our next lecture, Kepler's 3 laws. So I appreciate you taking the time to take a look at a little bit of a history associated with our understanding of the solar system. It is important because the work that Kepler did and the ideas that he brought to the table seem to us to be kind of tame, but they challenged a lot of basic conceptions. And then in addition, when we take a look at the history, it's a little more complicated than sometimes we're led to believe, and it's a little more nuanced than sometimes the stories say. So I appreciate you coming along with us. I hope I've made a little bit of scientific history a little clearer for you, and we'll catch you next time and talk about Kepler's 3 laws. And this one goes out to you, Aristarchus. Way to have the right idea off the bat.